welcome everybody on our Friday seminar. And today we're pleased to have Tim Kodalle here. He's a physicist working at the Molecular Foundry at the Advanced Light Source at Lawrence Berkeley National Lab. And he completed his PhD at the Martin Luther University in Halle and in combination with the Helmholtz Center in Berlin in Germany in 2020. And in 2021, he joined Lawrence Berkeley National Lab as a postdoctoral researcher and a fellow of the German Research Foundation. So, Tim, we look forward to your talk.
Thank you, Bram. Yeah, thanks for coming. As Bram said, I'm lucky enough that I work at two facilities at Lawrence Berkeley Lab. That's the Advanced Light Source and the Molecular Foundry. Both of them are open user facilities. The Advanced Light Source you might be familiar with. That's the local synchrotron radiation light source. There I work at a powder and micro diffraction beam lines. We do a lot of X-ray diffraction there. And then the other facility that I spend most of my time at is the Molecular Foundry, which is also an open user facility, but more on the nanoscale synthesis and characterization side of things. The Foundry consists of 6 different facilities. So there's 3 synthesis facilities. That's organic materials, inorganic materials, and biomaterials. And then there's an imaging facility, a theory facility, and a semiconductor nanofabrication hub. And all of these facilities, as I said, are open to public use. Like anybody can submit proposals. They get externally reviewed. And then if they get granted, people can spend up to 1 year at a time, completely free of charge, using all our instrumentation, our expertise, our computational resources, whatever they need. I personally work there at the inorganic nanostructure synthesis facility, mainly using Glovebox for perovskite, thin film deposition and characterization. And then we try to pivot more and more to robotic and automated tools for both thin film deposition, but also solution-based powder sample synthesis. And then I personally work a lot on developing tools for optoelectronic and structural characterization with a focus on in-situ characterization. So the way I try to leverage the advantages and disadvantages of both of those facilities is that I try to use the facilities at the Molecular Foundry to screen large parameter spaces of known or unknown materials as fast as we can, trying to identify interesting samples, which then can be analyzed in more detail in one of the other facilities. So, for example, we have a thin film deposition robotic system that can achieve fairly high throughput thin film deposition, and then we combine it with batch characterization, standard characterization like XRD, and optical characterization at the foundry to screen large parameter spaces. And we try to use machine learning more and more to automate and accelerate that even more. And then once we identify promising or interesting parameter combinations, we try to take those to the Advanced Light Source or also the National Center of Electron Microscopy, where we use in-situ structural characterization or spectroscopy or transmission electron microscopy to understand in depth why those samples perform well or show certain features that we're interested in. And yeah, today I want to show 3 examples of how we leverage these capabilities. The first one is going to be about cathode materials and lithium-ion batteries. The second one is a fairly recent project where we try to use closed-loop machine learning-driven experimentation to optimize tin oxide layers deposited by LD. And then the last one is going to be closer to perovskites, where I'll talk about structural property relationships in perovskite thin films. So I'll start with a cathode material project. In lithium-ion batteries, as you probably know, most of the cathodes that people use right now are NMC cathodes, so they're based on nickel, cobalt, and manganese as the transition metals in the cathode, and especially cobalt, but also nickel. It's just not very abundant. It's expensive, and it's mined under not so great conditions. So we try to replace them with alternative transition metals. Titanium and manganese are the candidates that we're looking at because they're both very abundant, easier to mine, and not as expensive. In a traditional layered cathode material, lithium and transition metals occupy different columns in the layered structure. Cobalt and nickel tend to stay on their sites in the structure for long times, I think several years, if you calculate it, versus titanium and manganese both have a high probability of occupying lithium sites once the cathode is delithionated. So discharging the battery means all the lithium diffuses out of that structure, and then both titanium and manganese tend to occupy lithium sites. And as you can see from the schematic here, the lattice will contract then, which limits back in diffusion of lithium, so charging the battery just doesn't work anymore after a few runs. In order to overcome that, one approach is to replace this layered spinel structure using a disordered rock salt structure, or DRX. And in this structure, each cation site has an equal probability of being occupied by a lithium atom or by a transition metal atom. And then when we delithionate that, there are not these individual channels that collapse, but it's just an overall diffusion process. And therefore, the capacity retention is much higher in those materials. People have already been making these DRX materials for the last few years. However, they use usually solid-state synthesis, and they have to go to fairly high temperatures to achieve this disordered structure, usually up to like 1200 degrees Celsius. Going to that high temperature means that the particles have a lot of time to grow, and therefore grow pretty large, like micrometer scale, which is not great for lithium diffusion during operation. So in order to make batteries from it, people usually have to use cost-intensive ball milling or jet milling processes to break down the particle size again after synthesis. Additionally to that, with a solid-state approach, you don't really have a lot of control over morphology of the particles. So we were thinking that if we could use our experience in solution-based synthesis and make these materials from solution, we might be able to reduce the temperature needed to achieve that DRX phase and therefore limit the particle growth. The approach that we chose was we dissolve precursor materials. I'll talk about that a little bit more in the next set. Make a solution, make a gel from that solution, then dry that gel, pyrolyze it, meaning getting rid of all the organic components, and then anneal it in inert atmosphere in order to get to this phase transition from layered structure to disordered structure. In order to achieve that, we have to scan a pretty large parameter space. There was basically no literature about the solution process when we started. So there's all these components, there's obviously a manifold of solvents we could use, combinations of solvents we could use, a lot of different precursors to introduce those three metals into the solution. And then on top of that, stoichiometry engineering, pH controlling, and all these additional factors that influence how the solution and therefore the gel and the final result behaves. For now, we've limited our objective of finding parameter sets that give us phase pure DRX material. And once we have that, we want to work on fine-tuning these parameters in order to reduce the transition temperature from the layer to the disordered structure. In order to screen this large parameter space, we utilized a robotic tool. This is SpinBot 1, which is a robotic thin film deposition tool. It handles substrates, usually glass when we work on perovskites, but in this case, when we work on oxides, we used aluminum oxide substrates. Can handle those. It has a pipetting module, so it can pick up pipettes, can mix solutions on a heater shaker, can also spin coat those solutions on top of the thin films. We have 3 different spin coaters there, and then move them to a hot plate. We have 2 hot plates in this setup for annealing. The platform is also equipped with optoelectronic inline characterization, that's PL, UV-vis, and PL mapping, which for the oxides we don't really use, but for other projects that's interesting as well. And then we combine this robotic automated deposition tool with high-throughput XRD. So this is a pretty standard XRD, but it has an area detector, which is nice. So we get information about orientation, and it has a batch measurement mode, so we can produce a large amount of samples with the robot and then program the XRD to measure overnight through large batches of samples. And therefore we can fairly fast scan large parameter spaces like the one I just described. So the workflow is as follows. We have this large parameter space, use the robot to, at this point we didn't really use any machine learning to just kind of randomly use, guided with a little bit of intuition, make a huge amount of samples that we then dry on the hot plate there, and then use the batch XRD tool to just measure a bunch of XRD patterns. And then from there, we pick the samples that are most interesting and then looked into those in a little bit more detail. And as an example for that, I want to highlight two samples where all the other parameters are kept constant and we just changed which solvent we used. So one is DMF and the other one is 2ME. And then we'll just go through what happens to these samples throughout the deposition process and what are the differences. So here on the left side is the case with DMF as a solvent, and on the right side the case with 2ME as a solvent. Otherwise, all the parameters are the same. And then from top to bottom, the first diffraction pattern is right after drying the gel. So that's just an amorphous silver gel. We don't see any crystalline signatures, so it's just amorphous material. And then when we undergo pyrolysis in air at 400 Celsius, in both cases, we see the formation of a mix of the layered spinel structure and the DRX structure. The main peak that identifies the layered structure is the one here at 18 degrees. And then when we calcinate at high temperature, we see on the left case, in the DMF case, that this peak that's characteristic for the layered structure disappears, versus in the case with the 2ME, that peak persists. So there's a mix of the DRX phase with the layered phase, and there's actually additional peaks here around 22. So there's a lot of impurities in that sample. And then in order to find out what might be root causes for this behavior, we took these samples to the beamline, the powder diffraction beamline at the ALS, and did in-situ XRD. So we anneal the samples from room temperature to 1000 Celsius and continuously measure X-ray diffraction. Every 30 seconds we get a 2D pattern. And then this is how it looks like over time for the 2ME samples. On the x-axis here we have the diffraction angle, and then on the y-axis the temperature. The peak here around 18, again, that's the one that is characteristic for the layered spinel structure, the phase that we don't want in the end. And then as you can see, there's a bunch of intermediate phases that appear during the process. Some of them disappear, some of them don't. And then if we just refine each pattern at a given temperature and extract the phase volume fraction of each phase and plot that over temperature, we end up with a plot like this. Starting from a mix of these two spinel structures, we heat up, and then around 840, which is roughly around the temperature when the DRX phase is thermodynamically more stable than the layered phase, we see how most of the material gets converted to the DRX phase, but some of it remains in these intermediate phases. And the DMF case, in contrast, starts very similar with a mix of the LMO and the LTO phase, and around 840 the DRX phase takes over. But there, around 870 to 900 Celsius, we get completely to phase pure DRX material. As you can tell, the main difference, other than that the DMF leads to phase purity, is the presence of this third intermediate phase, the titanium manganese oxide phase, which doesn't form in the DMF case, but forms in the 2ME case. So we obviously thought that that might be key to why one of the samples becomes phase pure and the other one doesn't. So we interrupted the process around 700 Celsius when these intermediate phases are present, and then did TEM mapping on the particles in each case. And as you can see, in case of the DMF, where we get phase pure material, we have a very well intermixed transition metals within each particle, versus in the case of the 2ME, where it doesn't turn phase pure in the end, we have strong segregation of the transition metals within a particle. So we think that on a very early stage, when we dissolve the precursors, in the DMF case, we really have on a molecular level intermixing of the precursor material, versus we have colloidal agglomerations in the case of 2ME, and that translates to segregation of the transition metals later on, which leads to the formation of this TMO phase, which then inhibits the complete transformation to DRX phase, at least at these temperatures. And then lastly, we made coin cell batteries from those to see how that translates in terms of specific capacity in the material. And as expected, the DMF behaves much better because it is phase pure, right? We get higher capacity in that case, better capacity retention over time as well. But we still have to work on the particle size reduction. You can see if we ball mill these samples, we obviously get much better capacity. So the next step is to interrupt these processes at earlier time. And in the case of the DME, we have some wiggle room there to just interrupt it at earlier times in the process at lower temperatures, and therefore hopefully don't have to do the ball milling process anymore. Okay, and then I want to move on to the second project, which is the closed loop machine learning driven atomic layer deposition. So for this, we customly built an ALD chamber, which is a vacuum chamber equipped with an in-situ ellipsometer that we use to monitor the film thickness during deposition. It's completely controlled through Scope Foundry, which is a Python-based platform that people at the Foundry developed. So it's completely open. It's all on GitHub, and we have control over all the mass flows and durations and pressures in the machine, and can therefore easily control the ALD growth. The goal of the project is not so much optimizing the material. We're working on titanium oxide here, which is a very well-known material, but kind of to understand how can we use a robotic tool together with machine learning in order to find a process window. And process window in this case, for those who don't know, means that we repeatedly go through ALD cycles, which means precursor dosing, then purging out of the precursor, reacting in an oxygen plasma, then purging out the reactants, which is one ALD cycle. And ideally, that will lead to the growth of one monolayer of titanium oxide. If we work below this ALD window, we wouldn't get complete coverage and therefore inhomogeneous growth. If we go too high in growth rate, we will get agglomeration of particles in the vacuum chamber and therefore to CVD growth. So we try to balance this and work in an ALD window. But as I said, that's not really the main focus here. People know how to do ALD titanium oxide. We just want to see how can we do that automatically, and can we use machine learning to guide this process. In this chamber, we have roughly 20 parameters that control the growth. Like a lot of them are pressures and durations of different steps and gas flow rates and things like that. And then we use this robotic control Scope Foundry together with Bayesian optimization approach based on GPCam, which is a Gaussian processing machine learning model, also publicly available on GitHub, to plan experiments, signal the parameters to Scope Foundry, which then translates them through PLCs to the robotic system and leads the deposition of the titanium oxide. And then here there's a first example where we are right now. In order to make it a little bit simpler in the beginning, we reduced this 20-dimensional parameter space to 4 dimensions based on our knowledge of ALD, which are like the most influential parameters here. And then we started using 5 random parameter combinations, 5 depositions, and then used those as the foundation for the GP to predict additional experiments. And then within 95 Gaussian processes, which takes us around 20 hours and is completely unsupervised, we can just let it run overnight while we're at home. The RMSE, so the root mean square error of the prediction, goes down to about 2% in terms of growth rate, which is the figure of merit here. And therefore, with an accuracy of around 2%, we can predict the growth rate in this 4-dimensional parameter space. So you're just trying to display it with 4 dimensions, not too hard actually. So each of these blocks is like 3 dimensions at a given dosing time, which means precursor dose time. And then in the color scale, we have the growth rate. And then, within 20 hours, we completely explored this 4-dimensional space. And you can see where the ALD window is. That's these like yellow areas on the third cube here. But you also have a good idea of what the growth rates in the rest of this parameter space are. And then just a different way of showing this data, like slicing through this 4-dimensional space in terms of pressure, just to visualize that it's pretty straightforward from there to see where is this ALD window and which parameter combinations one could use to actually deposit titanium oxide if that was the goal. And then, the last project I want to talk about is probably closer to what people do here, is about thin film perovskite layers. So as you all know, perovskites are interesting materials for photovoltaic devices. I probably don't have to tell you this. And one of the main issues is the stability. And one of the common approaches to improve the stability of perovskite layers is to introduce molecules that intercalate into the surface of the 3D perovskite, passivating it. And in our case, we used PACl, which is hydrophobic molecule, and is known to improve the stability of perovskite thin films. Usually people use a two-step approach, so they deposit the 3D perovskite using spin coating and annealing, and then add the surface passivation in the second spin coating and annealing step. And we were curious if we could reduce the complexity of this experiment by just combining both of those procedures into one and adding the bulky molecule, the PACl, into the anti-solvent step, and therefore reducing the experimental time by half. And then the questions were, does this still work? Does it still passivate the 3D perovskite? And also, what does the presence of the PACl during crystallization of the perovskite film do to the 3D perovskite? And then in order to answer those questions, we again used like a combined approach using both facilities. At the molecular foundry, we did in-situ transmission. So during spin coating and annealing, we measure the absorption of the material as well as in-situ photoluminescence. And then at the advanced light source, we combine in-situ photoluminescence, which therefore is our transfer vehicle between the facilities, together with in-situ X-ray diffraction. At the molecular foundry, we work in a very standard environment, just an inert nitrogen glove box. And there I built a setup that measures the photoluminescence continuously during spin coating and annealing. Here an example during spin coating. Once I drop the anti-solvent in this example, you can see how the PL signal evolves. And then when the crystallization starts, red shifts to the band gap of the material. And then on the right here is an example of using in-situ absorption. So once I put the substrate on the hot plate here, you can see how it turns opaque and the absorption edge in the UV-vis data emerges. And we can do it vice versa too. So we can do in-situ PL during annealing and UV-vis during spin coating. And then at the advanced light source, we build a setup that integrates both spin coating and annealing directly at the beamline. It's fairly compact. It's like maybe this big in total. The sample chuck holds the sample, does the spin coating, and then directly does the annealing afterwards. So on the same sample, we get both spin coating and annealing data. We continuously measure X-ray diffraction with a time resolution of about 1 second. So every second we get a two-dimensional diffraction image that we then integrate to get the patterns. And at the same time, we illuminate the sample with a laser and collect photoluminescence from the same sample. And then the whole setup is remotely controlled. It's in the beamline hutch because we're working with hot X-rays. So spin coating and annealing sequences are remotely controlled, automated, as well as liquid dispensing of the precursor solutions and of the anti-solvent is also remotely controlled. And then we did this whole procedure, all three in-situ techniques, on 2 samples in this case. One, the control sample without PACl in the anti-solvent. That's the one I'm showing here. And then afterwards, I'll show how it's different once we add the PACl to the anti-solvent. And then from top to bottom, we have in-situ UV-vis, then in-situ PL, and then in-situ XRD. And then down here at the bottom, you can see how the spin speed and the temperature varies throughout the process. So the first step is just spinning the precursor solution. So it's a wet film on the substrate. We don't get any PL or XRD signal from that. But then immediately when we drop the anti-solvent, and again, this is the control case, so no molecule in the anti-solvent, we see how the PL peak appears blue shifted at around 1.8 electron volts, which is quantum confined nuclei starting to grow. And then we see a fast shift of the PL signal to 1.65, which is the band gap energy of this composition here. That's the crystallite growth. And we see the same thing in the 100 reflex at Q equals 1 in the XRD pattern here. Fairly fast, this peak emerges. And then at the same time, we see the signature of a precursor solvent phase, which is present in the still liquid film during the crystallization of perovskites. As soon as we turn on the heat, so as soon as we start the annealing, this solvent phase disintegrates and the remaining precursor material converts into the perovskite, which you can see both in the in-situ absorption, where we see the shift to the bandgap edge of the perovskite, as well as the increase in intensity in the perovskite peak here. we lose the PL signal during heating just due to thermal quenching. And then comparing this to the same procedure where we add the PACl to the anti-solvent. In the first step, where we still just spin the wet film, we don't get any signature, of course. But then as soon as we drop the anti-solvent, we see quite a change in both PL and XRD signals. The PL still starts off with nucleation at 1.8 electron volts, but then the shift towards the bandgap energy is much, much slower than compared to the control case. And we see the same with the perovskite diffraction peak. And then additionally to that, we see that the signature of this solvent phase now is different. So it's a different phase when we add the PACl to the anti-solvent. And comparing with literature, this is a solvent phase that integrates some of the chlorine into the solvent phase. And chlorine is known to slow down crystallization in perovskite films. Once we start the annealing, the solvent phase still disintegrates, and we see significant perovskite growth. And additionally, later during the annealing, we see the formation of the typical N equals 1 and N equals 2 2D structures and quasi-2D structures growing at the surface of the perovskite. Additionally, we see that the PL signal retains better in this case compared to the control, so there is not as much thermal quenching in the case where we have the PACl, which is an indication for better crystal quality in this material. And then I think I'll skip this one. But then in order to check whether we actually have a improved crystal quality, we try to correlate the results using in-situ characterization. Here we did SEM on each of these films and then extracted the grain size distribution, and we see a slight shift towards larger grains in the case where we added the PACl, which correlates well with the fact that we have slower shift of the PL signal, meaning there is slower crystal growth, which usually leads to larger grains. And then that directly translates to larger lifetimes, or longer lifetimes measured by TRPL. So there's reduced non-radiative recombination due to a reduced density of grain boundaries in that film. And that directly translates to an increase in VOC, increase in fill factor, and therefore an increase in power conversion efficiency. And then in order to check whether the 2D material still does what we wanted it to do initially, we looked at the stability on the left side at elevated temperature, on the right side in humidity. And in both cases, the sample with the PACl in red shows much better stability. So not only were we able to reduce the amount of time needed to make these samples significantly by combining both of the processes, but we still retained the stability effect, and we got lucky that the addition of the chlorine specifically to the nucleation growth of the 3D perovskite actually was beneficial for that material. And then this spin coater, that was like 2.5 years ago, since then has been open for user operation at the Advanced Light Source. It's fairly modular and easy to use, fairly high throughput. We get around 10 samples done in a shift of 8 hours, where like a typical beam time is around 2 to 3 days, so 2 to 3 times 8 hours. And it's available for users since like 2023 and has been used by a lot of people, mainly from the US, but also from all over the world. And it is available for anybody to use. So if anybody's interested, please let me know. You can also submit proposals. And as you can tell from this, like people have been doing a lot of really good research, most of it on perovskites, and we're able to publish quite a bit there. And yeah, that's all I wanted to show. I'm happy to discuss in more detail.
Okay, thank you, Tim, for the great talk. If there's any questions? Oh, wait a minute. We have to get Rob.
Yeah, thanks very much for your wonderful presentation. If we apply for the ALS, the XRD, in-situ XRD measurement, how long maximum can we use?
So it's all proposal based, right? So you would first probably talk to the beamline scientist or to me, like what you want to do and if it's technically feasible. And then you write up your proposal, and part of the proposal is to justify how much time you want. So you have to make like a sample list ideally of like how many conditions you want to do and why it's important. And that translates to X amount of shifts. And then this gets externally reviewed, and the reviewer will tell us whether or not that is justified. And then we'll allocate time based on that and based on the availability of time. But typically people get between 1 and 3 days of beam time for this type of experiment.
Similar to others. Yeah, thanks so much. Thanks very much.
A question about the ALD work. So did you do the full exploration in one run, or was there sample loading and unloading?
So this was all done on one sample.
On one sample.
Mm-hmm.
Okay, and then so was the growth per cycle analysis was automated?
Yeah.
So the SE analysis was also fully.
Yeah, I mean
automated.
it's just ellipsometry, and so it depends a little bit on the quality of the model, of course.
Yeah, because because if you do everything in one run, that's potentially quite a complex layer. So.
Yeah, I intentionally cut this off at 100 runs because if we keep going, you can see that the RMSE actually goes up again because the growth does change quite a bit over time. Yeah.
Yeah, because we do a lot of ALD here as well, so you'll see a few ALD reactors on our level 4.
Sweet.
Yeah. And then for the multimodal analysis, are you also going to look into the dynamic modeling? Because there's a lot of beautiful information in there. So are you already doubling into that, or is it more the steady state or the end result you're looking at here, or are you going to look at the dynamics as well?
It depends a little bit. In this case, we just looked at what type of phases do we have and what is the main effect. But there are some other users that are interested in dynamics, especially like how fast do these intermediate phases disintegrate and what might be the diffusion processes taking place there, which is always a little bit more complicated, but we are trying to do that as well. Yeah.
I would say that's definitely should be a lot of beautiful information in there. We're not.
Thanks, Tim. Really fascinating and great to see such advanced work in this materials preparation and analysis. Can I ask what scale you're operating on in this? How big are the samples that we're talking about?
In this case here?
What's the average? What's generally the scale you work at, and what's the maximum you can work at?
So for this in-situ spin coater, we're very space limited just because of just because of space limitations at the beamline. So we're working on 1 by 1 square centimeter samples, which honestly is probably fine because the X-ray beam spot is just 5 by 100 micrometers. So making larger samples doesn't give us necessarily more information there.
Scan the beam so that you actually treat the
we don't.
There will be a message.
Oh.
Okay, we have to evacuate. Yeah. Sorry for that. Thanks, Tim, for the great